application node is based on the same principle. However, the neutral point is reconstructed then by software. The neutral voltage is equal to the average of the back EMF signals. Then, the reconstructed motor neutral point is compared to each back EMF signal to determine the zero crossing event. A zero crossing event occurs when the back EMF signals are equal to the motor neutral point. The challenge of this method consists of determining the correct time where the back EMF signals should be sampled, since the samples acquired by the ADC may be affected by the resonant transition voltage caused by the PWM switching frequency. These samples may be also affected by kickback currents produced by the windings de-energization. To avoid these noises, the DSP ADC is configured in such a way that it simultaneously samples the back EMF signals at a sample rate equal to the PWM reload frequency. The DSP ADC is also configured to take samples at the PWM on time with the purpose of avoiding the ringing noise produced by the electronic switches and other noises such as the high voltage spikes produced by the winding de-energization event. These noises could create false zero crossing events. The point in which the signals are sampled is variable across the PWM on time, depending on the motor speed. At low speeds, the DSP DSC device samples the back EMF signals at 50% of the PWM on time. However, the sampling point moves forward according to the PWM duty cycle to reach the maximum point of 75% of the PWM on time when the PWM duty cycle is equal to 100%. In this section, we will discuss the principle of digital filter, the majority detection function. This back EMF sensing method is based on a non-linear digital filter called majority function. In certain situations, it is also known as a median operator. The majority function is a Boolean function which takes a number of n binary inputs and returns the value which is most common among them. Let's consider a system with 3 inputs. The majority function of these 3 inputs will return whichever value, it could be true or false, occurs at least twice. In this case, 2 equal values represent 66% of the numbers. The majority function always returns the value of the majority of the numbers. The majority of the values can be expressed using 2 logic operators, AND or OR operators. As shown in the equation, it is the result of the OR value and the AND operation between A and B, A and C, and finally B and C. The implementation of this non-linear filter is based on a 6-sample window in which at least 51% of the 3 most significant samples should be equal to 1, and the 3 least significant samples should be equal to 0, for the purpose of identifying the occurrence of a zero crossing event in the digitalized back EMF signal. The first stage of the majority function filter is implemented using 2 logic operators, an AND operator for detecting the active back EMF signal correspondingly to the existing commutation state, and an exclusive OR operator is used to detect the falling or rising edges on the active back EMF signal. The values of the XOR and the AND mask depend on the number of the 6-step commutation sector, as shown in the tables. The active masked back EMF signal is then filtered using the majority function filter. This filter is implemented with an array compounded by 64 values and a special logic test condition that is used to modify the pointer to the next data array. This logic test condition also identifies both the falling and rising edges of the active masked back EMF signals. Both edges are represented as a true to false event at the output of the logical test condition. The output of this condition is also used as an input to the majority detection filter. The 64 values represent the 26 possible combinations that the 6-sample window could have for the active mask back EMF signal. Each value on the lookup table is a pointer to the next signal state over time. The filter is always looking for a true to false change at the output of the logic test condition. If this true to false condition is detected, the filter looks for 3 consecutive false states to validate that a zero crossing event occurred. A true to false condition at the output of the logic test represents a zero crossing event, and therefore a commutation on the rotor, which occurs after a delay. The 64 array values are determined as follows. The first 32 numbers are the index number multiplied by 2. The last 32 values are filled out subtracting 32 to the index value and multiplying the result by 2. There are 16 unique array index numbers that represent the true to false condition. These values are listed in order of appearance: 24, 25, 26, 28, 40, 41, 42, 44, 48, 49, 50, 52, 56, 57, 58, and 60. The values pointed by these unique indexes are replaced by 1 to indicate that a true to false condition has occurred. The 16 unique index values are selected using the following majority function criteria. An array index number is a unique value when its binary representation contains a majority of ones in the 3 most significant bits, followed by a majority of zeros in the 3 least significant bits. The 48 remaining array numbers are pointers to the unique values in case a true to false condition occurs. There are some values that never point to any of the unique values because they are not multiple of any of the 16 unique numbers. Those numbers that never point to a 16 unique number are then pointed to its multiple, and then they are trapped into a loop in such a way that the filter is waiting for a new value, which points to a unique number. The complete filter coefficients are shown in the following table. The first column shows the index value. The second column shows the calculated array value. And finally, the third column shows how the 16 unique values are replaced by 1. In summary, we have discussed the 6-step commutation technique used to control a brushless DC motor. We have discussed a sensorless method to control the commutation based on the back EMF signals. In order to precisely determine the commutation time, these signals are filtered using a digital filter based on a simple majority function. We have application notes on motor control. These documents can be obtained from Microchip's website by clicking on the DSP Digital Signal Controllers or Technical Documentation link. We also have Motor Control Design Center at www.microchip.com/motor. This wraps up the seminar on sensorless brushless DC motor control using a majority function. Thank you for your interest in the DSP Digital Signal Controllers.